Okay, so it's time, we'll just start. So it's really great to have Professor Krishnendu Sengupta visit RRI for the first time, and I hope he'll visit many more times in the future.
If invited.
COLLOQUIUM. So Krishnendu is a senior professor in Indian Association for Cultivation of Science, Kolkata. His work involves several aspects of theoretical condensed matter physics, including transport in topological quantum matter, ultracold atoms, and non-equilibrium dynamics. He did his MSc from IIT Kharagpur and PhD from University of Maryland in College Park. He was also in Yale and Toronto as postdoc, and then came back to India as faculty. He has received a lot of awards. He has been awarded the Shanti Swarup Bhatnagar Prize in Physical Sciences in 2012 and is a member of all 3 science academies. He also served as a council member of the Asia Pacific Center for Theoretical Physics between 2014 and 2017. And more importantly, he has been a great source of inspiration and influence on younger researchers like us in related areas. So, yeah, I'm happy to tell this over to Krishnendu.
Okay, thank you, Shobhan, for the invitation and for this very generous introduction. I wish it was true, but no. But okay, let's get to this. So today, what I intend to do is to provide a sort of a story for how this field of emulating strong correlation using ultracold atom platform has evolved. And of course, I'm going to pick and choose topics. This is not going to be a comprehensive story, but I hope that it will give you some perspective of how things were in the early 2000s when it started and how it has evolved since then. Okay. So here is a brief outline of the talk. And so the first part is some basic features which is really bread and butter of everybody who works in this ultracold atom systems. And then I'm going to talk about 2 platforms. One of them is this tilted lattice, where there is some theory that we did long back and some experiments that followed. And then, of course, the Rydberg chains and arrays, which are recently subject of intense research. And this would be like the part which is about emulating strong correlations in these systems, and you will see why. And then I'm going to switch gears a little bit and go to the last part, where I'm going to talk about some aspect of dynamics in these cold atom systems. And one of the reasons for saying this, that this is by far the most isolated system that you can ever prepare in a lab, completely cut off from its surroundings. And therefore, watching effects of quantum dynamics in this kind of systems is something which is possible. In a standard laboratory, it's very hard to do this without effect of environment. And that's why this is what makes these platforms unique in terms of dynamics. Okay, so let me start with this part 1. So, this whole thing started with cooling atoms, and of course we have our own perspective about how cold things are. So in Calcutta, if the temperature goes to something like 15 degrees or below, people take out their monkey caps and stuff like that. Now, that's a human perception of cold. And you of course know that freezing point of water is 273 Kelvin or 0 degree centigrade, and that's where things starts feeling really cold at a human scale. But then you go to the laboratory scale, where liquid nitrogen gives you something like 77 Kelvin, liquid helium gives you 4 Kelvin. And these are the typical condensed matter laboratory scales that, when in ancient prehistoric times when I was a PhD student, these used to be the cold scales in any laboratory. Okay? Maybe a few millikelvin and stuff like that. That's where you could get to. But ultracold atom changed all that, and with techniques like laser cooling and evaporative cooling, you could get into temperatures which is roughly like a nanokelvin. And that, just to get a perspective, is the coldest known place in the universe. Because if you think of outer space, that's like the microwave background radiation, which is like 2.7 Kelvin. That's sort of an average temperature, and here it goes to nanokelvin temperatures. But the question that really strikes you when you first hear temperature like that what do you do to measure this? You cannot just stick in a thermometer there and try to measure it. It will simply heat up the entire system and destroy everything. So what typically people used to do, and still probably what people do, is that they take some bosonic atoms, and at this temperature, almost any atoms, but particularly things like rubidium and sodium atoms are used, they would form a Bose-Einstein condensate. You have cooled it enough so that the bosons have gone into this coherent state. And our undergraduate theory on this Bose-Einstein condensate tells you that if you look into the occupation of atoms of different momentum states, of course, at zero temperature, absolute zero, that would be a delta function. Everything is going to go into the k equal to 0, the zero momentum, zero energy state. But typically at finite temperature, there would be a peak with a width. And that width is essentially the measure of the temperature of the system. And this is the technique that people can typically use to see how cold these things are. And I'm going to come to how people measure this momentum distribution in a moment. So that's that. And the thing to realize here is that it's a bit different from our standard laboratory practice in the sense, both in sense of the temperature that is being created and also in the sense of how things are measured and what people do with this kind of things. So the cooling techniques, and I'm pretty sure there are lots of people here who knows this much better than I do, but just for completeness, let me just say this. So you typically take a bunch of atoms in some trap, and the first set of cooling is this Doppler cooling of atoms, where you point lasers to it. Now, when you put a laser light towards an atom, the atom only interacts with this laser, absorbs this laser when its frequency matches with the energy difference of its states. Otherwise, it just lets it pass. Now, this is the thing that is used for this Doppler cooling. So what people typically do is to sort of use a laser whose frequency is a little bit less compared to the energy difference between the levels of the atoms, and we typically say it's a bit rate detuned, in the sense that it's detuned by a amount which is smaller than this energy difference between the two levels. So what happens is that when this atom and photon essentially move towards each other, if you are sitting on the photon, you are going to see, sitting on the atom, you are going to see that the photon comes with a slightly enhanced frequency because of Doppler shift, and that makes it resonant. And so the atom preferentially absorbs photons which is moving towards it, and this reduces its momentum. But after absorbing this photon, the atom of course goes into an excited state. It doesn't remain there forever, it just comes back and emits the photon. But the basic point is that that photon is emitted in any random direction. It's completely random. So on the average, after many, many such events, what happens is that there is a directional decrease of momentum because it only interacts with photons which is moving in one direction. And therefore, its momentum, average momentum, and therefore energy and temperature decreases. So this is one way to cool down this collection of atoms. And this is what leads to creation of what is known as optical molasses. And you can go into order microkelvin temperatures using this technique. Once you have this, the second technique that people use to sort of cool these things is known as evaporative cooling. So what happens is that you take a bunch of these cold atoms in a magnetic trap and you slowly remove the top of the trap. Now this axis, which is the height of the trap, is also the energy axis. And if you do it correctly, which experimentalists know how to do and I don't know how to do, apparently with some specific rates and stuff like that, the energetic atoms at the top of the trap, they just leave the trap. So you get a decrease in the number of atoms, but its average energy decreases. Since average energy here is a measure of temperature, you see that this thing becomes really cold, and it's possible to achieve temperatures order nanokelvin using this technique. And I think the record now goes well below nanokelvin, tens of picokelvins or something like that. That's what they can achieve in different laboratories. But these two cooling technique essentially allows you to go into a temperature regime where you can safely call that to be as low of a temperature, almost a zero temperature state. And therefore, without worrying about thermal effect, you can talk about having quantum coherent effects at really low temperature. So this is a great platform for studying low temperature physics in correlated systems. So one more thing which is required for getting into a correlated system with this kind of atom photon system is to create strong correlation. That's something that one needs to do. And the ingenious way of doing this is that you apply counter-propagating lasers to this atomic trap. So what happens is that these atoms feels a potential because they have a polarizability, which goes as the intensity of the laser light. that you put in. And if you tune the frequencies right, this A could be a positive number, this polarizability A or alpha or whatever you call it. And therefore, these atoms would preferentially sit at the bottom of the track. Okay. This situation is similar to having a bunch of particles hopping on a periodic lattice, but here you create the lattice with light. And these atoms can be bosonic. And in fact, in the initial experiments, they were all bosonic. So this allows you to look into, in condensed matter language, block theory with bosons, because you have a periodic structure created by light, and you have a bunch of bosons hopping there. Okay. And, okay, so, but if this lattice is really, really deep, you know, what happens is that it becomes difficult for these bosons to hop from one side to the next. And therefore, its average kinetic energy compared to whatever potential energy it has, that ratio goes down. Okay. And as a result, you could get into a situation where the atoms are very strongly interacting, you know, because the kinetic energy is much lower than the interaction. So this technique gives you a way of looking into this, you know, strongly interacting systems, which is on a periodic lattice. And this is the experiment which showed this uniquely. So here, the experiment is such that what they do is that they take these cold atoms in a trap, and then they switch on this optical lattice by putting in a laser. So they pump up this laser to some intensity of Vmax or V0, okay, out here, over a ramp time of roughly 20 milliseconds, with a rate of 20 milliseconds, and then it allows the system to stabilize in here for about 20 milliseconds, and then they dropped both the trap and the laser and let the atoms fly out. So that was the experiment. So after the atoms fly out, what happens is that they have the screens on which they strike, and they take that picture, you know, where the atom has struck on the screen. Yeah. Absolutely, yes.
So because these are not electrons which hit the screen, so they are imaged on the camera.
They are imaged on the camera.
So you have a probe light which is falling on the camera, it passes through the atom, and the absorption of the atom is detected on the camera.
Yes.
It's different from the electrons.
Oh no, I didn't mean this to be the electron this thing. I'm just skipping over details, but I agree. That's absolutely correct, actually. So here is a, you know, picture of that, getting the image of these bosons on the camera using this. But the interesting thing here is that you see that after you have dropped the trap and switched off the potential, the flight of these bosons is roughly a free flight, you know. And as a result, the position of the boson on the screen or on the camera plate or whatever, after some time is completely determined by its initial momentum or velocity. Therefore, if you look into the distribution of these bosons on that screen, you are going to find a picture of the distribution of the momentum of the bosons inside the trap. So this, yeah, just one second. This position distribution therefore reflects the momentum distribution of the bosons inside the trap, and this is how they measure the momentum distribution of a boson and determine whether it's in a superfluid or a Mott insulating state. Yeah, sorry. Yeah, I'm coming to that, why the absorption is maximal there. Yeah, so I'm coming to that, just give me one second. So here is the case when this potential is, you know, you haven't turned on any potential, so the typical expectation is that everything is in a superfluid state. So if it is in a superfluid state, the number of atoms would be maximal at the k equal to 0 momentum, okay, which is the center of this. So the position distribution essentially, since it just reflects the momentum distribution, it just shows a central blob at the center of the screen. Okay. Now, as you increase your V0, you know, you turn on a lattice, and so you have these satellite peaks because the lattice has now a separate periodicity. But something interesting happens when this lattice strength is reasonably large. This central peak disappears, which means that you really don't have a collection of, a macroscopic collection of bosons at the k equal to 0 state anymore. On the other hand, at around V0 equal to 20 here, these are all smeared out. So what it means is that it's completely delocalized in momentum space, its occupation, which by uncertainty principle means that inside the trap they are very, very localized. Okay? And therefore you see a superfluid to a localization transition with the critical point being estimated at the point where this central peak vanishes. And that is an example of a superfluid insulator transition from a superfluid state to a Mott insulator state. And since this happens at a temperature which is at least 2 orders of magnitude less compared to other scales in the problem, this is an example of a quantum phase transition, where it's really this depth of the lattice which is bringing out this transition by tuning the effective interaction string. So here is a picture of this interference pattern and absorption images, and here is some other fancy pictures. But let's now come into this question as that suppose we understand this phenomenon, how do we model it? Okay. So the model typical, somebody had a question? So the model typically that people use for this kind of situation is a single band Bose-Hubbard model. And what people say is that, well, the simplest way to picturize this is that within each of these optical lattice, we have an energy band. There are, of course, multiple bands, but other bands are way higher compared to any other scales in the problem, both U and this hopping. And the Hamiltonian has two terms. One, because the these bosons can hop from one neighboring site to the next. That's sort of the kinetic energy terms of these bosons. They can move from site to site. And the other, because there is an interaction between these bosons. Now, this interaction is, of course, a very short range because these are not charged electrons or anything. So they are typically approximated by an on-site interaction, where an interaction potential shows up only if there are 2 or more bosons on a single site. Okay. And then this is what constitutes a Bose-Hubbard model. And typically for theorists, what people do is to put in a chemical potential so that they can tune the density. That's just a theoretical construct. And people study this model to understand this quantum phase transition that comes in. Now, why do this model shows a phase transition to begin with? And there is a very simple way to understand this. So imagine that I look into this in a regime where my optical lattice is really, really deep. Okay? And therefore, my hopping strength from one lattice to the other, which goes as exponential of minus this lattice strength, is really small. Okay? And let me set it to 0. Then your Hamiltonian just has this interaction term and a chemical potential. And if your chemical potential, and this is really easy to calculate, I'm not going through the details, but it turns out that if your chemical potential is between 0 and U, then the ground state consists of 1 particle per site. Okay? That's the Mott state. So this is with the assumption that you have integer number of particles per site, and this will, so if it is if mu goes between U and 2U, the state is with 2 bosons per site and so on. So there are these different, so let's concentrate on this stable ground state between, when mu is between 0 and U. Now the question is that if I now lower my lattice, how this state destabilize? How am I going to get another state which is different from this thing? And a typical way to see this is to create possible excitations. So imagine that I take this state and I put in a small particle out here. Now to put in this particle, I have to pay an energy cost because it will cost an energy U, and you are going to gain an energy mu because you have added a particle. Okay. But once you have paid that energy cost, once this particle is out here, it can freely hop from one side to another. It doesn't cost an extra energy for it to be here instead of there or there. So it can freely hop and lower its energy. And that lowering of energy is roughly can be estimated to be the hopping strength times the coordination number of the lattice. The coordination number being the number of nearest neighbors, because it can hop in so many directions. So it depends on that coordination number. But now you see that this excitation energy becomes negative at some point when this T is large. Now what does that signify? So if you are doing a perturbation theory and you get a correction to your energy which is negative, you should really throw away your calculation. That's certainly not something that happens. But here it signifies something physical. What it tells you is that the ground state from which you started your perturbation calculation and calculated this energy is not the real ground state anymore. In other words, this excitation energy going to 0 signifies this destabilization or instability of this particular Mott state. So this critical hopping, which comes from setting this to 0, essentially tells you a rough position of where the Mott insulating to superfluid transition can take place. And similarly, you can remove a particle from this Mott state and get critical hole hopping. So if you take out one of these, this thing can hop from side to side. That is, other bosons can come and fill in this thing. And it's really the minimum of these two which gives you the critical hopping. And this, really naive argument has been formalized and made better in several ways. So Friedrichs and Monian, in a very influential paper, essentially sort of included higher order fluctuation corrections to this argument. There have been mean field theory, which was first developed by Michael Fisher in '89, and Tivier wrote a very interesting paper, Tivier and collaborators, Tivier, Krishnamurthy and others, I think, in '93. There have been extensive quantum Monte Carlo studies, the first one done by Nandini Trivedi and Kraut, and all of this essentially verified this qualitative picture that there is a transition, a quantum phase transition between a Mott and a superfluid state with the dynamical critical exponent of this transition being 1 at the tip of the Mott lobe or 2 at some other positions. And the reason this happens is at the tip of the Mott lobe. So I showed you, I showed you that there is a critical hopping. So there is a cost of adding a particle versus cost of adding a hole. These are typically not the same. So what it means is that there is no particle hole symmetry in this model. It's different to add a particle than to remove one. But there is one point in your parameter space, and which is typically the tip of this lobe right out here, where these two energies become similar. And this extra symmetry, this extra emergent symmetry is what changes the universality class of this transition. The dynamical critical exponent changes from 2 to 1. And that's some interesting, effect of this symmetry. Okay, but in all of these things, there is hardly any information about the nature of the Mott phase. It was all taken to be some garden variety, unit occupation state. So what we did at some point is to look into a Green's function formulation of this, which can access this density distribution even within the Mott phase. And here, something interesting shows up, is that if I look into the momentum distribution of these bosons, deep inside the Mott phase, it's of course flat because there are, in every position and therefore at every momentum, there is a fixed number of bosons. Okay? However, as you approach the critical point, there is a precursor showing that there is a build-up of this peak around k equal to 0. It doesn't abruptly happen at the superfluid transition, but this build-up, what is known as the precursor peak, can be captured in a relatively simple calculation. And apparently the height of this precursor peak matches experiments pretty well. This was done in Hans Spillman's group in Maryland, and apparently, you see that both deep inside the Mott phase, where that peak is almost non-existent, and near the critical point, in everywhere, the red, which is the theory, and the black, which is the experiment, essentially matches very well. The mean field theory is given by the red dot, and that deviates from the, this thing. So, okay, so this is roughly about the first transition that people have seen in this kind of platforms, that is the cold atom platform, realizing Bose-Hubbard model. But once people sort of looked into this, the question that was asked is that, in many cases, one sees interesting phases in symmetry broken quantum systems where there is translational symmetry breaking. This is something like, for example, an antiferromagnet, or other states where there is some symmetry breaking. And people started asking, is it possible to have this kind of phases in these cold atom platforms? And there were many candidates. I didn't want to go into the details of this, but one possibility is to have two species of these bosons and to interact with each other, and they give very interesting antiferromagnetic phases, where antiferromagnet means that one species of boson is realized on one site, and then other species is realized on the next site, and you just have this up-down combination. The other thing that people tried is to put in a next nearest neighbor interaction and then get some CDW kind of state, translation symmetry broken state. But the point is that these are notoriously difficult to get in the experiment. It's not so easy with the standard cold atom platform. So what worked is this technique where people have applied an artificial electric field. Now, what does it mean to apply an electric field to these bosons? Because these are neutrals, you just can't put in a standard potential. So what it means, there are two ways of doing it. The first thing you can do is to shift the center of the trap holding the bosons, because this trap is like a harmonic oscillator potential, and once you shift its center, it's like a shifted harmonic oscillator potential, which gives a linear term, and that linear term is just like a potential to these bosons, because the electric field, if you will, gives exactly similar linear term in the Hamiltonian of any system. Okay, so that's one. And the second thing is that many of these species of bosons, particularly this 87 rubidium, is spin polarized. And therefore, if you can apply a Zeeman magnetic field, which has a special profile, linear special profile, that can also act as an effective electric field for these bosons. Once again, because it gives the same linear potential in its Hamiltonian. So these two are the typical techniques that people use to get this electric field. And the Hamiltonian then has the standard Bose-Savart model, but in the presence of this electric field. So this is a technique for generation of quote-unquote electric field for neutral bosons. Okay. It just means that you put a linear term, a term in its Hamiltonian which varies linearly in space. Okay. So this is something that Emmanuel Bloch and his group did in this 2001 experiment. So here what they did is the following. They again ramped up this optical lattice potential, but here they put in this tilt, okay, which is called this perturbation, and they let the system be there with that perturbation for about 20 milliseconds. After this, what they did is that they ramped down this optical lattice to a value such that the bosons for that value of this optical lattice potential would be in the superfluid state. Okay. Now, they let it there for a few milliseconds, and then again they drop the trap and everything and measure the momentum distribution. The idea is that if the bosons, while being in this state, has absorbed some energy and got into some excited state because of this perturbation, then when it comes to this superfluid state, it's going to retain that energy, and therefore its atoms are not going to be at k equal to 0, but at some finite k. Okay? And more the energy absorption, more the difference between these two peaks at k. And the reason you have two peaks is that k and minus k are similar. There is, and therefore the width of this, the difference of this peak is essentially what you measure. So this width, and it's a measure of how much energy you have absorbed. So the point is that here in this V0, if you are in a superfluid phase, okay, then there is a linear pattern of this absorption and then it saturates. So you can absorb energy continuously as you increase the time at which you have put this perturbation or the amplitude of this perturbation. However, when you get into this mod state, see here that there is a resonant energy absorption. That is, it seems that the system preferentially absorbs a lot of energy provided you have a particular value of this perturbing potential. So these two situations are clearly different, and therefore something interesting is happening to the quantum state here if it's in the mod phase and if you apply an electric field. And this is something that one needs to understand to get into the physics. Yeah.
In the absence of interaction, that
Interaction, you mean in the absence of the potential? This U term.
Yeah.
Yeah.
So this will show block oscillation, right?
This will show block oscillation.
So,
But the bosons will be completely localized, right?
so now how to think like that new phenomena due to this U?
Oh, but the bosons will be localized in both cases. For large U because it's a Mott insulator, and for small U because this thing is just an electric field.
I'm saying like in the absence of U, you have block oscillations.
Yeah.
And block oscillations means you will have oscillations.
No, but in real space the boson wave function will be completely localized.
Even,
Yes, because the reason is that this is a, if you look into this, another way of looking into this is that it's a one-year Stark problem. And you know that the solutions are just Bessel functions, and those are more than exponentially localized in real space for large E. Large electric field. Okay. Of course, the localization length is going to become larger and larger if you decrease the electric field. That's there. But it's a localized problem. You see, this is where these quantum particles are different from classical things. Think of a ball and a bucket situation. Applying an electric field is just like tilting this system of buckets. You have a potential. So if it's a classical particle, all the balls are just going to move and go to the last this thing. This is not what happens for the quantum case. In the block oscillation language, you have reflection from the edge of the Brillouin zone and it just comes back. So in that sense, it's localized, because it doesn't travel to arbitrary momentum or anything like that. However, there is also another way of understanding it in terms of this one-year Stark problem, where you can exactly solve the problem and you see that the particles are completely localized.
But then if you put U, you will get those features, right? Extra peaks which you are trying to.
That's right. That's right. So there is a reason why that happens, and let me come to that. Okay? That's the whole point, actually. So now to understand this, why this happens, we started to construct an effective Hamiltonian, effective model. So we started from this parent Hamiltonian, which is a U and a hopping term and this electric field. Okay? And we are going to work in a regime where this hopping, we are in the Mott phase because that's where this resonant absorption works. So my hopping as well as the difference between this U and E is much, much less than either the electric field or the interaction potential. So that's the regime that we are going to look into. And one thing to note is that this is a regime which you can never access in standard condensed matter laboratory. The reason being is that if you wanted to get an electric field this strong, you are going to see electric breakdown straight away. Okay, so this is something which is really different for this system.
Yeah, so it's actually not in block oscillation regime.
No. This is not. But the point is that if U is 0, it's in the block oscillation regime, but it can still be local. Yeah, if it's a strong electric field, you can sort of get a. No, as I said, I mean, you shouldn't be thinking of it in a band structure way. You should think of solving the problem entirely, and that gives you this one-year Stark ladder, with localized wave function. Okay, so it's going to be very much localized in this. It's just going to scan through Brillouin zone and come back every time. Okay, so now you see, as with the bosons, now we can try to think up to, suppose we are in the original Mott state, how can energy be absorbed? Now, can I create this quasi-particle and quasi-Hall excitation? And the answer is no, because if I create one of these extra quasi-particles, it cannot hop anymore, because its effective Hamiltonian has a hopping term, but it also has the electric field term. And therefore, it's completely localized. It cannot reduce energy by hopping from one side to another. So this doesn't work. What works is that it can form these dipoles, because if it goes from one side to the next, this combination of one vacancy out here and one extra particle out here, that has an energy cost of U minus E, because you pay an extra energy U by putting this extra particle here, but creating this hole here, essentially, you lose an electric energy. So, sorry, you gain an electric energy because you have moved to this side, and you lose because it costs an energy. So this combination, the hole here and this extra particle here, that's a dipole, essentially, because it's a hole and a particle combination with energy U minus E. Okay? And these are resonantly coupled to the parent Mott state when U is equal to E, because there it doesn't take much of an energy to create a dipole. Okay. So then we can say that, okay, so since we know that these are the low-lying excitations, how can we create an effective dipole Hamiltonian, which is going to determine the physics of this system? So one term in this dipole Hamiltonian, which is absolutely trivial to understand, is that it costs an on-site energy of U minus E to create or destroy a dipole. Okay, because creating a dipole is just simply U minus E. So this is like the chemical potential for these dipoles. However, there is also this other thing, because of this extra, because of this extra possible hopping, you can spontaneously create or destroy a dipole, because particles, the original bosons can hop from one side to another and form these dipoles. So there are these dipole non-conserving terms. So this Hamiltonian doesn't conserve dipole number. But most interestingly, there are these constraints. So you can form only one dipole on a given site, because if you try to form more, you will see that that costs a huge amount of energy, because either E or U do not match with each other. And the second thing is that if you create a dipole out here, you cannot create one in the next site. So this is a configuration where there are two dipoles on neighboring site, and this is like moving a particle from one site to two sites to the next. That costs an energy U minus 2E, which is not a part of this low energy resonant. So these two are the constraints. One is that you can only have one dipole per site, and the other one is that the number of dipoles on neighboring sites, their product is always 0. So if you have dipoles on one side, you cannot have it on the other. Okay. So this is the Hamiltonian, and we aim to determine the phase diagram of this Hamiltonian. So apparently, okay, what is the ground state? The ground state essentially is a dipole vacuum. Okay, if U is much, much greater than E, because then, creating a dipole means that you have a large positive energy cost, and your ground state is the one in which there is almost no dipole. Okay. But the strong electric field case, where the electric field is large compared to U, there the ground state is the one with maximum number of dipoles. But notice that, this maximum number of dipoles has an interesting feature. You can have dipoles between odd sites or the even sites, but not both, because you cannot have dipoles on neighboring sites. So there are two equivalent ground states where the dipoles are formed either on all odd sites, or odd links rather, or on even links, okay, between two sites. And therefore, this is exactly similar to an Ising model, where in the ferromagnetic state you can have all up spins or all down spins, and it really doesn't matter which configuration you choose. So this ground state essentially, which spontaneously chooses one of these, breaks a Z2 symmetry. It's exactly like a ferromagnet breaks a Z2, Ising ferromagnet breaks a Z2 symmetry by choosing all up or all down states. This is exactly similar here. And the behavior is very similar to that of an Ising model in a transverse field. And when we looked into this numerically, we find that an intermediate regime. So in the strong electric field, we find a ground state which is a Z2 broken symmetry, which is a discrete symmetry breaking. In the weak electric field, there is no symmetry breaking. The ground state is unique, it's just 0 dipoles everywhere. And therefore, these two ground states must be separated by a quantum phase transition, because there is an additional symmetry which is broken. And this is what we exactly found by doing exact diagonalization on these systems. And in those days, exact diagonalizations can be done only with computers with 1 GB RAM. So understand that it was not that straightforward to do n equal to 18, we somehow managed. But the point is that once you do this, you find that there is a Ising criticality sitting in between. And this is one of the realizations of a completely different phase transition, which is typically ascertained to spin models and everything, in a completely different platform in some sense. And then 10 years later, there are some experimental measurements. The problem with this situation is that everything was within the Mott phase. And in those days, in the early 2000s, the only measurement that people could do was this momentum distribution measurement of bosons. But in the Mott phase, it didn't give you much of an information, because everything was smeared about the entire momentum, this thing. So you really couldn't distinguish between a situation where there is one particle per side versus two particles per side. In other words, the structure of the Mott phase was not accessible by this momentum distribution measurement. So people came up with something ingenious. So what they did is that they could, much later, they could project the square optical lattice on, on some magnetic trap potential and their ampler lattice depth. So what they did is that after the step is prepared, they suddenly increase the lattice depth to a very large value. So this means that all dynamics freezes, because there is no hopping anymore, because you have killed this hopping by increasing the lattice depth. And then they apply a light with a special frequency in such a way that if you have an even number of atoms inside the trap, inside any of this lattice site, they can interact with this light and scatter with each other and go out of the trap. So at the end of this light assisted collisions that takes out and eject pair of atoms, one can image the remaining atoms by and what one can detect is, if there is a signal, this must mean that there was an odd number of atoms, so that at least one atom was left in the trap. And if there was no signal, there is an even number of atoms. So they could detect parity of occupation of these atoms. And this was good enough for measuring this kind of transition, because the number of atoms changes by 1 in both sides of this dipole. And this is what they did. So they realized this tilted Bohr-Savart model, and they mapped this dipole model into some spin language. But let me, without getting into the details of this, let me just show this. So they have this single readout scheme where there are situations where you have everything glowing, which means that there are 1 atoms per side. And this is this, you see, and this essentially means that there are no dipoles, which means that you have a state with 0 dipole or 1 boson per side. And here, in the other large electric field limit, they see a situation where there is no sites with any bosons, and that has 2-0-2-0 pattern, which means that dipoles have been formed. Okay? So in their language, this is of course like the antiferromagnetic site, and this is sort of a paramagnetic site and stuff like that. But this, in some sense, is really this Ising transition, showing this going from 0 dipole to a maximal number of dipoles on given sites. And they could do this, and they could go back and forth through this, showing that it's indeed a quantum phase transition that happens. And this is of course a finite this thing, so the drop is not that sharp, but this was taken to be a signature of this possible transition.
Sorry, what was the peak that I forgot?
I'm sorry?
That peak site peak you were showing
Which side?
in the previous.
Okay, sorry.
Yeah, this one.
This peak? Oh, that is because if you increase your electric field further, then you can get into a regime where U minus 2E also becomes a part of this resonant subspace. Okay. Here, so essentially, that peak is smaller, but you could get into. So we were mainly working in this regime where this U minus E is. Oh, there, what will happen is that you are going to have a dipole, which is a particle and a hole separated by 2 sides. That's another possible phase, but we really didn't explore that phase. This is all ground state, yeah. Okay, so how much time do we have? 15 minutes, I guess. Yeah, so, okay. I'm going to just talk about this Rydberg chain and then probably end. And that's, so, okay. So let me get into this other platform, which has been very much subject of active research. These are the Rydberg platforms where you take this 87 rubidium atoms, whose ground state has the following configuration. and the excited Rydberg state, which is another stable state, but it's quite excited, essentially is 71 s half. It's hugely large atomic number. So essentially, what happens is that you can couple this ground state to a Rydberg state by a collection of lasers, and you don't exactly match the energy difference of these atoms by these lasers because you don't want really it to absorb all the energy. So you put in a small detuning, which is difference of this laser frequencies with the difference of the energy of this ground and the Rydberg state. Okay, so that's typically called delta. That's called the detuning, and this detuning could be tuned to be either positive or negative depending on what you want to do. So in that situation, what is the typical effective Hamiltonian? So every site essentially has a detuning. So this tells you how easy or difficult it is to excite the atom from the ground to the Rydberg state. So if this detuning is positive in my language, then it's relatively easy to sort of excite this. And if it is negative, it's difficult. Okay? And this Ni is the density of Rydberg excitation, how many atoms you have excited to their Rydberg state. But these Rydberg states have another essential property, that if you have two atoms in nearby Rydberg state, the interaction between these two atoms is essentially goes as one of this 1 over R6 potential, and this V essentially is the amplitude of this interaction, which is a tunable parameter in experiment. And also one can vary this detuning. And apart from this, there is another term which has a spontaneous emission or excitation because of these lasers from the ground state to the Rydberg state. So these three terms, the interaction term which gives you this Rydberg excitation between these Rydberg atoms, the detuning term which tells you how easy or difficult it is to create a Rydberg excitation, and this thing which creates a spontaneous coupling between this ground and the Rydberg state is what determines the low energy effective Hamiltonian of this kind of systems. So the thing is that because of this interaction, there is a very interesting phenomenon that happens in this system. If your V is large, what happens is that if you have excited one Rydberg atom on any given site, there is a radius within which you don't want to excite another Rydberg atom. That's prohibitively energetically expensive. Okay, and therefore a Rydberg excitation on any site creates a radius around it where there would be no other Rydberg excitation, and this phenomenon is known as Rydberg blockade, because one excitation blocks other possible excitation on neighboring sites. And in this case, we are going to be interested in a regime where the neighboring site falls within this blockade radius. So if you have one Rydberg excitation created on a given site, then the neighboring sites cannot have a Rydberg excitation because it's energetically prohibitively expensive. So, and in fact, that has been realized in experiments in Marcus Grainer's lab, and they have seen this thing where they can create these maximal Rydberg excitations on either odd or even sites, but not both. And this happens when you tune this detuning to a large positive value, because it's like, you want to create the maximal number of Rydberg excitations. And this is very similar to this tilted dipole model, because just as you wanted to create a maximal number of dipoles, here you want to create a maximal number of Rydberg excitation. But this constraint here, which was there because of you cannot create dipoles at neighboring links, here it comes from the fact that you cannot create two Rydberg excitation on neighboring sites. Okay. So this is the same thing which enforces a Z2 order state. Now you can increase your Rydberg blockade a little more, and you can get a Z3 order state because you cannot create a Rydberg excitation on two neighboring sites and so on. Okay. So apparently, okay, so I'm going to come to this picture a bit later, but apparently, as it turns out, that there is a way to map all this into the dipole model, and one can create a model like this. And in the literature, it's typically called the PXP model, and people have worked with this and got the phase diagram, nothing different. The interesting thing comes when you look into this in not a 1D Rydberg system, but people have created these 2D Rydberg atoms. And on a square lattice, it turns out that this can give rise to various symmetry broken patterns. This is from Subir's work in 2019. You can have a staggered phase, you can have a checkerboard phase, and others. And more interestingly, there is a paper from Ashwin's group which showed that if you arrange this on a Kagome lattice, if this 2D array is a Kagome lattice, but with the sides of the lattice sitting on the center of these Kagome bonds. So this is sort of like the, a complementary lattice to the Kagome, not exactly the dual, but close to that. And this lattice is called the Ruby lattice. If you just join the midpoints of the Kagome and try to form a lattice, that's called a Ruby lattice. And here they identified a spin liquid phase, in between. And because this is not a bipartite lattice and one expects that kind of thing to happen. And there is a theoretical suggestion that one could get into a spin liquid phase using these Rydberg platforms. Okay, so this is one sort of way that you can get into this really strongly correlated phases, non-trivial phases using these cold atom platforms. So I'm not going to get into the dynamics in details because running out of time. So in the interest of time, let me just show you one small thing and stop there. Okay. So basically, what happens in this kind of Rydberg system? So let me just get into this plot first. Yeah. So let me come here. Okay. So you see, another experiment that this Marcus Greiner group did, which created a lot of excitement in the field, is that they prepared this lattice in the ground state where you have this Z2 ordered ground state. Okay? So you essentially create a situation where the ground state is such that you basically have a Rydberg atom on every alternate side. Okay? But then what you do is that you suddenly change this detuning very fast compared to all other timescales in the problem and make it 0. Okay? So that you don't have any detuning anymore. Okay? Very close to 0. You cannot make it exactly 0, but it's very close to 0. And then you see how this state evolves. Because this is of course a ground state in the presence of strong detuning, but it's not really an eigenstate in the absence of detuning. So, this is like saying that I have an initial state and now my state is going to evolve according to some Hamiltonian evolution. And that Hamiltonian is just this term and the interaction term. Okay? So what you expect typically in this situation is that that system is going to have some dynamics and then approach a steady state. Because it's a non-integrable model, that steady state is supposed to be thermal, and you get some effective description of that. And typically in this kind of strongly interacting system, you expect this time to reach this steady state to be order 1 in some typical time scale of the system. So, and that typical time scale is order, I would say tens of nanoseconds or something like that. But here, after a few microseconds, which is huge time scale compared to the typical time scale of the system, you see that there are always these oscillations. These oscillations, of course, die down, but it persists for a very long time. So this is not the typical expected theoretical behavior for non-integrable system. What you expect is that the system is certainly going to go to a steady state value within the first few, maybe tens of nanoseconds or something like that here. That doesn't happen. So people tried to understand why this thing happens. And the answer to this is that it turns out that in this Rydberg situation, in this Rydberg system, there is a class of states which is completely different from the typical states in the Hamiltonian. These states are called quantum scars, and they are labeled by the fact that even though they are sitting right in the middle of the Hilbert space, where typical states show quote-unquote thermal behavior, which means their entanglement entropy essentially is volume law and all that. Here, they have anomalously low entanglement entropy, and they typically have some approximate emergent symmetry, which doesn't let them mix with the rest of the thermal states. So once you start your dynamics in a state which has a large overlap with one of the states, which is the case with this, this antiferromagnetic state, the dynamics sort of progresses by this subspace rather than proliferating in the whole Hilbert space. And that's what gives rise to these oscillations. And you see that these oscillations occurs only when you start from the initial Z2 state, which is this blue curve. If you started from the initial vacuum state, which is like all no Rydberg excitation anywhere, that's another possible state where you can start in. Thermalization is immediate. You see that there is some little bit of oscillation, and here, you know, it just goes in out here. So this is sort of the expected theoretical behavior, and this goes in by the name of eigenstate thermalization hypothesis, which predicts this kind of behavior. And this class of states, which are atypical states, essentially leads to violation of this eigenstate thermalization hypothesis in this kind of systems. So dynamics starting from an initial state, which is either Z2 or 0, can be plotted, and you see distinctly different behavior. This also means that the final state of the system, or at least the approach to the final state, depends strongly on the initial memory, which is another way of seeing that standard statistical mechanical expectation is violated in this kind of system. So this constitutes one of the, you know, experimentally most experimentally most well demonstrated situation of violation of eigenstate thermalization hypothesis. And this also makes this kind of systems a really nice platform to study this kind of effects and others, you know, which I'm pretty sure will be very common in coming days. Okay, so I think I'm going to stop here. And so to summarize, I mean, you know, these platforms provides an alternate way of realizing both strong correlation and study effect of non-equilibrium dynamics in closed quantum systems, particularly because their parameter regime is such that you can have strong correlation, and also that they are so far separated from the rest of the environment that you can maintain quantum coherence for a very long time. And therefore, these are really nice platforms. And I think there will be many more interesting effects in coming years in this kind of studies. So I think I'll stop here, and thank you for your attention.
Questions?
Hi. So apart from this time of flight measurement on cold atoms, what are the other detection scheme that we can
one
do?
of this is imaging after sending in this light, that thing that I showed.
Okay, so it's a scattering of light.
Yeah, so what you do is that, okay, so very broadly, send in this light so that, you know, even number of atoms just fly away from this step, and then you image the rest. Okay, and then you detect whether there is a atom in a given trap site or not.
So, I mean, after I give photon, it inject out something, then after that I still do time of flight measurement, right?
No, not really time of flight. You take a picture of that.
Okay.
So that distribution. So again, I mean, you know, you basically can see the absorption pattern, and that's what. Sorry, let me just. Yeah, you see that if you don't have, so if you have a single this thing, you can see that there is a signal, and if you have something. If you have even number of this thing, after this, everything will be empty and there will be no signal. I mean, that's how you distinguish this.
Thank you.
Yeah, sure, please.
So it's not only like absorption, you can also have fluorescence imaging, like you shine.
I think this one is fluorescence imaging.
This is fluorescence because absorption is the most appropriate when you have a large number of atoms with very high density.
Yeah, sure.
Then you have significant absorption of the beam, and then you can image that absorption on a camera. With very good signal to noise ratio.
No, this one is fluorescence. Yeah,
But when
right.
you have very small number of atoms, absorption will give almost no signal because single atom does not have any absorption. So it's mostly the fluorescence. So it's there's a light from all direction, which is also optical molasses, which is shining on the atoms, and it cools the atom and also images it. So it does not let the atoms heat up the system. So it's doing the two things. It's imaging the fluorescence of the atom on the camera and also cooling down the atoms so that it prevents heating up of the atoms during the imaging.
Okay.
So
Yeah,
that's...
thanks. that's helpful. Yeah.
In the Rydberg case where there is sudden quenching, what do I expect in physical space? How do I imagine this? So what is happening? I have these optical lattices, I have atoms sitting in optical lattice potentials. Yes. Now I have quenched, I have I've gotten rid of the Rydberg detuning. So what do I expect to see in physical space?
Physical space, there would be a distribution of Rydberg excitation across this thing. In the steady state, that's going to be a constant distribution over time. Okay. But how it approaches steady state, the distribution of n is going to fluctuate.
So the number of sites which are excited with Rydberg excitation will show similar oscillations?
Depends. I mean, what spatial pattern is there. Usually, these kind of things are global. Okay. So the spatial structure is not very important in the sense that every site will show somewhat similar, or every even or every odd site is going to show something similar. The odd and the even sites are different because you have broken that symmetry by having an antiferromagnet. Okay. But if you take two even sites, it doesn't matter where you take them in the chain. Okay. Their correlations, etc., are roughly similar.
Okay. I have another. Can I ask another?
Sure. Please go ahead.
So it's just my naive understanding, because the system is so cold, any dynamics which you induce in this system will show very long time scales, right?
No. Here the time scale is determined by the interaction time scale, and it can be pretty quick. So it can reach steady state. In fact, you expect it in this strongly interacting regime to reach the steady state very quickly. So within the first few 1/omega time scale kind of thing.
I understand. So this is, as a function of temperature, if I ask you to say how this will grow, what will you use?
As a function of temperature, I don't really know, I haven't worked that out, but the point is that what I would expect is that as you increase your temperature, this coherence is going to go, temperature is going to destroy this coherence. But the point is here, that's a time scale we can safely ignore, because it's at least 2 orders of magnitude lower than all other time scales in the problem. So, yeah. So, not in this, but so there has been studies where, in the original Bossavard model, when people have got into this Mott insulating phase, people have tried to see what happens if you increase the temperature there. Okay. And there is a melting from a Mott to a thermal state, thermal insulator kind of this thing. That I know in the initial days people have studied, but here I don't really know. But I'm pretty sure that this oscillation, the quantum coherent part, is going to go. Yeah. So that's going to be flattened out because of this.
Thanks.
Yeah. So, okay, I don't know the full generic answer, but one possibility is that if you have emergent symmetry, which is obeyed by a class of state, typically order L number of states in a L size system, which is much, much smaller than exponential L, which is the total Hilbert space dimension. Then they form a separate subspace within your Hilbert space. And if this happens, and in a dynamics, if your initial state, has overlap with one of these, this emergent symmetry do not let you mix the dynamics with the other state in the Hilbert space. And therefore, you can have an oscillating dynamics for quite some time. Now, the point is, most often this emergent symmetry is approximate, like here. It's almost SU2, but not quite. And the upshot of all that is that from this subspace, there is a leakage term, so that in the long time, this thing goes away. So this is really system dependent. And maybe there are some more generic understanding of this, but to the best of my knowledge, if I give you a system and ask you whether there would be scars in there, unless you can do the calculation for that thing, I don't know of a general principle. So just to complete this, can I take 2 minutes to answer this? Here is a simple example that I can show. It's a spin 1 chain. Okay, so spin 1 XY chain in a magnetic field. So here you see the ground state, let me assume, is all minus Sz equal to -1. But now, if I act on this with this state, S plus square, see, on any site R, I create a plus minus pair when I act on this. But if I do this in such a way that if I act it on an even site and if I act it on an odd site, they come with the opposite sign, it turns out that this term acting on that kind of plus minus pair just gives 0. It will both give 0, 0, but with an opposite sign, and that just cancels. So then you see it's only the SZ term that lives, and then you have a tower of states with this energy, where n is the number of such pairs that you have created. So this provides a spectrum generating algebra in some sense, and that gives you this SU2. In fact, these operators forms a spin L/2 representation of the SU2 algebra, and then everything is like different from the standard ETH prediction. So this is one of the simplest system where you can see this kind of scarce states. Yeah, but the beauty of it is that this symmetry here it's exact, but in general more complicated system, even if you have an inexact symmetry. So for example, if you could have this SU2, but then a small SU2 breaking term, the effect of that term in dynamics shows up at a much longer time scale. Before that, you still see this SU2 symmetric behavior, which essentially tells you that there is a scar-induced phenomenon. So scars can be approximate. I mean, that's there in that sense actually.
To ask one question, so
Yeah.
you showed an example where it's on the Ruby lattice for the Rydberg PXP model. You said there is a spin liquid phase. So when we think of spin liquids, we typically think of some frustration where all the bonds cannot be satisfied and so on.
Yeah.
So what is playing the role of frustration?
Here you have this, this interaction inducing this constant. Okay, so you can have this excitation only in neighboring sites and all that. So think of this as realizing an antiferromagnet and trying to do this on a non-bipolar lattice. That will create the frustration.
It's like on a triangle you cannot.
Yeah, exactly. It's the same. It's a bit more complicated than that, but the basic physics comes from that.
Any more questions?
So, scar states are originally detected or originally was discovered in classical system.
That's right.
So there they say like
the Buminovich Stadium, and I take pride in sort of being able to pronounce that name correctly. But yeah,
Heller, right?
Yeah.
Eric Heller. Okay, so now I'm saying like those are like which have classically stable periodic orbits.
That's right.
So similar things people must.
No, so you see there is a history out there. So the first thing is that those are like single particle effects. Okay, so what happens is that in the classical case there are these periodic sort of orbits which do not fill the whole Hilbert space. Then I think it's Eric Heller in 84 or 85, something like that. They tried to do something very interesting. So they took this stadium, which is like a rectangle followed by cylindrical ends, semicircular ends. So and then they said that look, what I'm going to do is that I'm going to take this as a potential in a Schrodinger equation, and I'm going to see what happens if I take a wave packet whose center is on one of these special trajectories, and I evolve with this. How does the probability distribution evolve as a function of time? And they saw that if the center of that wave packet is right on that, is near the one of these several trajectories, the probability distribution doesn't fill out the entire phase space. Phase space in the quantum mechanical sense, So the point is that then this is a violation of ergodicity, right? Because you do not fill in everything. So that is sort of the classical scar and its single particle quantum equivalent picture. Here it's a bit different. Here the thing is that it's ergodicity violating. That's the connection.
No, I'm asking, like let's think about Wigner space or Buscemi space and try to have something for such systems.
Yeah. So there are some work on classic, I think it was a 5-4 field theory or something like that, where they were trying to design this kind of things. But these with this strongly correlated thing, it's very hard. I don't know a way of doing it actually. Because, in a many-body system with L sites, how do you even come up with this? So any first quantized notation, it's very, very hard out here.
And about that, in the Bose-Hubbard model, you had one dipole, like particle movement created the dipoles.
Yeah, so a single hop, but no more.
Yeah, but hole also created one kind of dipoles, you said, or what you were saying that.
No. Dipole is essentially a hole on one side. So think of the initial Mott state as a same number of particles on every side. Let me take that to be 1 for simplicity. Then if I create an empty thing on one side and 2 particles on the next, that empty and the extra particle is what forms a dipole. Okay, that's the dipole. But for the initial Bohr-Savart model, what I showed is that in the absence of electric field, where there are no dipoles or anything like that, if I put in an additional particle or an additional hole, what's the energy cost of doing that? If that's what you were asking. Yeah.
Thank you.
Okay, so I think if you have more questions, you can free to discuss outside. There are snacks outside. Let's thank Krishnendu again, and we have a token of appreciation from RRI.
Oh, okay, thank you.
I thought even this Marcus Kleiner group on